Hello friends, welcome to another tutorial in network analysis and synthesis. We are starting up a new series where we are going to discuss three-phase circuits. In today's tutorial, we'll introduce three-phase circuits, we'll study the common configurations, and we'll talk about the advantages of three-phase circuits, and we'll continue the discussion in the coming tutorials. Now, three-phase circuits are more complicated than a single-phase circuit for sure, but they provide numerous advantages over a single-phase electrical system, and we are going to discuss that. We are going to see how complicated the things become when we migrate ourselves from one-phase circuit to three-phase circuits. The definition of a three-phase circuit is it may be considered as a three separate single-phase systems. So these are the key points here, and they are phase displaced from each other by 120 degrees, and the peaks of the respective voltages do not occur simultaneously whenever they are subjected to the load. So when we talk about a three-phase circuit, the graphical representation would look something like this, where we have three voltages represented by, of course, the red, the yellow and blue. And if you look at these voltages, they all have the same amplitude, but they are phase displaced from each other by 120 degrees. So the peaks are not occurring simultaneously. So the first thing that you notice about a three-phase circuit is that at almost all instances of time, the voltage which is being offered to the system is pretty high. You can see if we talk about the average of the availability of the voltage to the system, it is pretty high. So it never goes down to a significantly lower values closer to zeros as it used to go in the single phase electrical systems. So this is one evident advantage, but with these advantages there are going to be a lot more complications also. The advantages are enumerated here. They are pretty economical because the conductor material needed to transfer the same amount of power is less for a three-phase system. There is a single neutral that cuts the costs, and it is versatile. This point can be understood with the fact that both domestic and industrial commercial powers can be provided from the same source. So voltage regulation is pretty easy. I wouldn't say easy, it is better, and it is a self-starting system. The torque produced is pretty high, and for the similar frame size, that we would have used in a single phase system, for that similar phase size, it will offer a much greater output power. So the frame size, you can say, is reduced significantly. Now, as far as the configurations of three-phase circuits are concerned, there are two popular configurations, and most of the numericals or most of the questions, they originate from this classification of three-phase networks. This is pretty important from the point of view of examination. Star and delta. A star configuration or a star connection of electrical system will have a neutral, and that'll have a neutral point, and all the voltages they will be connected to that neutral point. I'll draw that and I'll show that graphically. So this is how a star connection would look like. So we have three voltages, R, Y and B. So this can be thought of as ZR, this is ZB and ZY. Well, that'll come much later in the discussion, but for the time being all the voltages are being connected to this point, this common central point, and this is known as the neutral point or the star point. And the voltage from this point to this neutral point is VNR, and this will be VNB, and this will be VNY, and these are known as phase voltages. Now this is most important term. So I'll say VNR, VNY and VNB are phase voltages. The reason is pretty simple, that all these voltages, they are connected to the same grounded neutral or the star point. So they can simply be termed as VR, VY and VB. In most of the books, if you see this nomenclature, that will refer to the phase voltages. And in a balanced star configuration, we'll find that VR, if let us say is V angle 0 voltage, then VY will be V. The amplitude will remain the same, but it will be displaced by a phase of 120 degrees. We know that this is going to happen, and VB will be displaced in the other direction, or VB will look something like this. Alright, so these expressions, they correspond to this graphical representation of voltages. If we see that VR is starting from 0, then VY is 120 degrees displaced. It was starting earlier, or it was starting late by an angle of 120 degrees, but this is how it'll look like. And the vector representation of phase voltages will be something like this. So all of them are phase displaced from each other by 120 degrees. Now please understand, we are talking about phase voltages. We are not talking about the voltages between the two lines, because this is one line, this is another line, and this is the third line of the three-phase circuit. So this is the phase voltage, and phase voltage essentially involves the voltage of a particular line with respect to the neutral point. It is super important to understand that phase voltages, they correspond to the voltage of a line with respect to the common star neutral point. However, we can also find the voltage between VR and B, VB and Y, and VR and Y, red yellow, blue yellow and red blue, and they are going to be known as line voltages. The concept of line voltages actually originated from delta connection, which I'm going to discuss now, the delta connection will look something like this. Now please understand, these lines, red, blue and yellow, they were being offered to the system, but they got to a point R, B and Y points where basically it's the terminating point of two impedances connected together, and it is the node of two impedances connected here. So the voltage between these 2 points, they'll be known as the line voltages, as we know that there is no central point of reference with which we can measure the voltage. So this is going to be the voltage. So if I say that this current is IRY, BR, sorry, and this is IRY, and this current is IBR. So these voltages, if we calculate between these 2 points and these 2 points and these 2 points, they'll be known as the line voltages, which are represented as VRY. Of course, this will be V reference if we want to say it, and the other one will be displaced by an angle of 120 degrees, and the third one will again be displaced by an angle of 120 degrees in the other direction, or we can say minus 240 degrees. So this is how a delta connection will look like, and of course the delta connection offers the line voltages, and in a balanced delta connection, please understand, it is super important to understand that we are talking about the balance conditions here for the sake of simplicity. Balance means that these impedances are going to be the same. If these impedances differ, then of course the currents will also differ, and the voltage will be uneven. So for the sake of simplicity, in the coming lectures also we'll restrict our discussion to balanced star and balanced delta networks, but this is all I wanted to discuss in the introductory lecture of three-phase circuits, where I wanted to introduce the common configuration star and delta, and they offer voltages known as phase voltages and line voltages. They look something like this. Star offers a neutral point, delta does not. And in the next lecture we'll talk about the relationship between the phase voltages and the line voltages in star connection, then in delta connection, and so on and so forth, and then we'll proceed on to do numericals. And I hope this tutorial was of help. If you liked the content, give it a thumbs up, consider subscribing to the channel, it'll be a great help. I'll see you in the next video. Till then, take care, bye bye.